Welcome to the SAR channel, where sound and audio are demystified. Early personal computers were basically programmable calculators with almost no sound features. They had only a small speaker that could make simple beeps, and creating music on them was nearly impossible. As hardware and software improved, computers became much better at handling audio. Sound cards with synthesis chips and ADDA converters made it possible to play MIDI files, record, and playback wave files. Multi-channel speakers and subwoofers also became common. Personal computers adopted audio formats like CD, DVD, Blu-ray, and 3D audio, and used computer technologies such as PCIe, FireWire, USB, and Thunderbolt. These developments combine different technologies to bring higher sound quality and more advanced features to computer audio and multimedia. Today, personal computers serve as the main hub for both professional and home recording studios in many fields. The PCI Express, PCIe, is a fast and efficient connection system inside a computer. It offers high data transfer speeds, strong resistance to noise, and smooth communication between the computer's processor, memory, and connected devices. For audio, it's important that the data flow is never interrupted. Thanks to its high performance, the PCIe bus enables shared signal processing, where the main processor and the audio accelerator work together to handle audio tasks efficiently. The Institute of Electrical and Electronics Engineers, IEEE, formed a team to create a new way to transfer data between devices. Using Apple's original FireWire design, they developed the FireWire High-Performance Serial Bus Standard. This standard defines how the hardware and controller work for both internal backplane and external serial connections, allowing fast, low-cost, and versatile data transfer. The Universal Serial Bus, USB, was created to replace older serial and parallel ports, offering a faster and easier way to connect devices while solving the problem of limited interrupt availability for peripherals. The USB on-the-go feature was made for portable devices like phones and cameras. It lets them connect directly to each other without a computer, allowing one device to act as the host or the peripheral and switch roles when needed. It also includes a smaller connector and low-power design, replacing many special-purpose connectors used in docks and slots. USB OTG devices follow the USB 2.0 standard. USB works very well for sending audio signals. It uses standardized audio transport methods to keep driver setup simple and includes strong synchronization for steady data flow. Although USB supports asynchronous transfer, higher bandwidth devices like audio and video use isochronous transfer, which reduces jitter but adds a bit of delay. To keep audio channels in sync, each audio device reports its internal delay, caused by buffering or signal processing, to the system. The host then uses this data to align all streams accurately, keeping phase jitter within ±1 sample. USB is widely used for audio connections in many practical situations. Created by Intel and Apple, Thunderbolt is a very fast connection technology that carries data, video, audio, and power through a single cable. It combines the features of PCI Express and DisplayPort into one serial connection, enabling quick and flexible communication between computers and external devices. Thunderbolt allows several devices, like audio interfaces, monitors, and storage drives, to be linked in a chain while keeping full speed for each one. It transfers data both ways at the same time, reaching speeds up to 40 gigabits per second in Thunderbolt 3 and 4, which makes it ideal for professional audio and video work that needs low delay and high stability. It also offers accurate clock timing, very low data jitter, and power delivery through the same cable, reducing clutter and improving overall efficiency. Most computer motherboards and sound cards include AD and DA converters, and both hardware and software tools that let users record and play stereo audio at different sampling rates. They can play sounds using wavetable synthesis, recorded samples, or FM synthesis. These systems usually offer digital inputs and outputs, a software-based audio mixer, built-in amplifiers, and often analog line-in and line-out, SPDIF in-out, microphone input, and ports for game controllers or MIDI devices. Sound cards fit into an expansion slot and come with software, including essential device drivers that control all the audio functions. Stereo playback creates a typical concert-like sound where audio mainly comes from the front. However, it can't reproduce ambient sounds that surround the listener, which reduces the sense of space and realism. This problem is even worse on personal computers, where speakers are usually placed close together. To create a more immersive experience, different processing algorithms can adjust stereo signals so that sound from two speakers seems to come from all around the listener. Personal computers with proper hardware can also play true 5.1 channel surround sound for a more realistic sound field. The audio codec 97, AC97, also called modem codec 97, MC97, is a standard that defines a two-chip design used to deliver high-quality audio on personal computers. It is commonly built into motherboards, modems, and sound cards to provide advanced audio features. The high-definition audio, HD audio, standard improves on AC97 by supporting more audio channels and delivering higher sound quality. It defines the system design, programming interfaces, and data format used for communication between the host controller and the codec through the PCI bus. Intel introduced the HD audio specification in 2004. In the DOS environment, programmers could easily access system functions to fully control audio and video features. But Windows made things more complicated. The Windows Multimedia API gave access to sound card functions, but developers couldn't directly control hardware. They had to use the limited tools provided by Windows. To fix this, Microsoft created the DirectX API suite, designed to support high-performance multimedia development on Windows. DirectX gives real-time, low-level access to devices used in demanding audio and video applications. It organizes multimedia functions into components such as Direct Sound 3D, Direct Music, Direct Show, Direct Draw, Direct Play, Direct Input, and Direct Setup. Some companies created single-chip solutions to reduce the audio processing load on the main CPU. At the same time, computer processors themselves have become increasingly capable of handling complex multimedia tasks. If you've enjoyed this video so far, please hit the subscribe button for more. Thank you. Connections like AES-3 send digital audio data in real time. In other cases, data transfer can be faster or slower than real time, so defined file formats are needed to include both the main content, called essence, such as audio, and the extra information about it, metadata, such as edit lists. This makes it easier for one or more people to work on projects smoothly and transfer content between different systems. Some file formats are also designed for streaming, where audio, video, and other media types are mixed together. Media data like audio, video, images, graphics, and text are called essence, while the data that describes them is metadata. Metadata includes details like sampling rate, number of channels, and downmixing options to help decode the content. It can also contain search data, copyright, ownership, and instructions for combining and synchronizing different elements, sometimes called composition metadata. Sometimes, audio is stored as raw data files containing only amplitude samples with no header. But usually, structured file formats are used to ensure compatibility between systems so that audio can be stored, transferred, processed, or played correctly. These files include a header with metadata such as sample rate, bit depth, number of channels, compression type, title, and copyright information. Many formats also include extra metadata. Most audio programs can open both raw and encoded files and convert them to other formats. The waveform audio format was introduced with Windows 3.1 as the standard for multimedia sound. It follows the resource interchange file format, RIFF structure, and is often called RIFF WAVE. WAVE is one of the most common formats for uncompressed audio, supporting mono and multi-channel files at different sampling rates. RIFF files organize data into sections called chunks. The main RIFF chunk identifies the file as a WAV file and gives its total size. The format chunk describes technical details like sampling rate and bit depth, while the data chunk holds the actual audio samples. WAV files can store both PCM and non-PCM audio. The broadcast wave format, BWF, is an open format developed by the European Broadcasting Union, EBU, and is based on WAV. It adds extra features and restrictions through a broadcast audio extension chunk that stores details such as creator, creation date, sequence, and timecode. Each BWF file is time-stamped with 64-bit precision, allowing files to be placed accurately in order without using an edit list. BWF typically uses a 48 kHz sample rate and 16-bit PCM resolution and supports multi-channel MPEG-2 audio. It defines settings like surround layout, downmix options, and channel order. Multi-channel data is stored as separate monotracks rather than interleaved ones. BWF files share the same .wav extension and can be played by any system that supports WAV. Extra data chunks are ignored. However, because BWF can contain either PCM or MPEG-2 audio, some players may not play MPEG data saved with a .wav extension. The AES 46 standard extends BWF for radio broadcasting, adding a CART chunk for labeling and playback control information such as cues, timing, and level references. MPEG audio data can be stored in AIFF-C, WAV, or BWF formats with the right headers, but most of the time MP3 files are used directly with the .mp3 extension. In these files, the data is made up of a series of MPEG audio frames, which allows playback to start from any point by finding the next frame. Many MP3 files also include an ID3 tag that stores information such as the song's title, artist, and genre. The AIFF audio interchange file format with extensions .AIFF or .AIF was originally developed for Macintosh computers, but is also used on personal computers and other platforms. Based on the EAIFF 85 standard, AIFF supports various types of uncompressed audio with different numbers of channels, sample rates, and bit depths. The format includes details about channel count, sample size, and sample rate, along with the audio data itself, all stored in chunks like WAV files. AIFF is still used for some Mac sound files and is supported by many editing programs. QuickTime.mov is both a file format and a multimedia system extension originally for Macintosh but now cross-platform. It can store and play back video, audio, animation, and MIDI data in sync. Because video has its own time base, it can control preset actions or triggers. QuickTime movies can contain multiple audio tracks or be audio only. Using QuickTime's export feature, users can create MPEG-4 compatible files, and any .mp4 file with MPEG-4 video and AAC audio can play in QuickTime. With compatible hardware and software, users can record video, cut unwanted parts, compress, edit, add sound, and save the final project as a QuickTime movie. The software can be used for offline video editing or to generate edit lists with timecode, and it supports real-time playback and streaming. QuickTime also handles MIDI data for playback. A Windows version allows Mac-created presentations to play on personal computers. The audio-video interleaved format is similar to QuickTime, but is designed specifically for Windows systems. Ideally, audio and video projects made on different workstations would work perfectly across all platforms. The Open Media Framework Interchange, OMFI, was designed to make this possible. OMFI is a group of file format standards for audio, text, images, graphics, animation, and video. It also defines how editing, mixing, and processing data are described so that both the content and its edit information can be shared between systems. The format includes details about media sources, sampling rates, and timecode, and it supports both compressed and uncompressed files. Files can be created in one system, edited or processed on another, and returned to the original format without losing information. An OMFI file contains everything needed to create, edit, and play digital media projects. Usually, native files are converted into OMFI format, transferred to another system, and then converted back into the target system's native format. OMFI is also designed so that playback can happen directly from the interchanged file if both systems are similar. It efficiently handles large files by locating and reading only specific pieces of data, like source information, instead of loading the entire file. Files can also be updated or modified without having to completely rewrite them. OMFI later evolved into Microsoft's structured storage format, forming the basis of the advanced authoring format AIFF. The OMFI system was originally developed by Avid Corporation. The advanced authoring format AIFF was developed as the next step after OMFI. Introduced in 1998, AIFF is an open-source standard for exchanging media and metadata in professional post-production and authoring work, not for final delivery. It allows content and metadata to be shared between multiple users, systems, platforms, and applications. AIFF defines how content elements relate to each other, places them on a timeline, synchronizes different streams, describes processing steps, tracks file history, and can link to external media not stored in the file. AIFF also includes version control, keeping a record of edits as the file is modified. The AIFF Association, which oversees the format, was founded by Avid and Microsoft. The Material EX change format, MXF, is a media file format used to exchange program content in professional post-production and authoring. It provides a simple, platform-independent container for both media, essence, and metadata, and is closely related to AIFF. MXF files are made up of frames, with each frame holding audio, video, data, and frame-based metadata. MXF can store various media types like MPEG, WAV, AVI, or DPX, and MXF files can be linked to AIFF projects. Both MXF and AIFF share the same internal structure and use the SMPTE metadata dictionary for workflow and data definitions, though MXF uses a simpler metadata system compatible with AIFF. AIFF files may contain only metadata referencing essence stored in MXF files. MXF allows partial retrieval, so users can access only the parts of a file they need without copying the whole file. Its sequential temporal format enables real-time streaming or standard file transfers. Because data is stored sequentially, MXF is often used for finished projects and media delivery. MXF was developed by the Pro-MPEG Forum, EBU, and SMPTE. The AES-31 standard is a set of open specifications for exchanging audio data and project information between devices like workstations and recorders. It supports both simple transfers of single audio files and more complex exchanges that include editing information from different systems. In AES-31, a universal resource locator, URL, can point to files on various media or platforms, specifying the file, host, disk, folder structure, and file name with a .wav extension. Digital audio extraction, DAE, is the process of copying music from a CD directly in digital form, without converting it to analog. A CD or DVD-ROM drive reads the data and creates a file, like a WAV file, on the computer. The resulting copy is a bit-for-bit duplicate of the original. This process is often called ripping, which generally means copying music into digital files. If you've learned anything new so far, please like the video. It really helps the channel grow. Thank you. Portable flash memory provides a small, durable way to store data on non-volatile solid-state memory, EEPROM, using a built-in controller. There are many types of flash memory with different shapes and sizes, including compact flash, memory stick, SD cards, and more. Some cards plug directly into a device, while others connect through USB or other interfaces. flash memory can store many gigabytes of data, uses very little power, and does not produce heat. Personal computers and dedicated audio workstations both rely heavily on magnetic hard disk drives to store audio data. Hard drives provide quick and random access, fast data transfer, large storage capacity, and low cost. Using hard disks, audio systems can combine storage and editing functions, making production more efficient. While optical disks are useful for storing static data, magnetic hard drives are better suited for the fast, dynamic workflow needed in audio production. Magnetic media is made of a base coated with a thin layer of magnetic material like gamma ferric oxide, which contains tiny cigar-shaped particles. Each particle has a permanent magnetic field that can be switched back and forth. In unrecorded media, the particles' magnetic fields have no overall alignment. To record data, an external magnetic field aligns the particles according to the applied field. The strength needed to change their orientation is called coercivity, and not all particles respond equally. Some align with weak fields, more align as the field grows, until the media is fully saturated and cannot change further. Saturation magnetic recording is used to store binary data. The external field is strong enough to orient nearly all particles. When a bipolar waveform is applied, the media has two states of opposite polarity. The right signal is a current that flips polarity at each bit transition, causing regions of particles to align positively or negatively. These polarity changes represent binary zeros and ones. During playback, the read head detects changes in magnetic orientation, generating a signal that reproduces the recorded waveform. Strongly recorded signals produce clearer data with fewer errors. Saturation recording maximizes the difference in particle orientation, making the recording robust and reliable. Hard disk drives provide reliable storage, fast access, quick data transfer, large capacity, and random access. They can store many gigabytes of data in a small, sealed, low-cost unit. Most hard disks are non-removable, which lowers production costs, simplifies the design, and allows higher storage capacity. The disks are usually rigid aluminum alloy, stacked on a common spindle, and coated with a magnetic layer like ferric oxide over an aluminum oxide undercoat. Some disks are metallic with a thin magnetic layer, which allows tighter data tracks, higher density, and faster access. Thin film disks are harder and more durable than oxide disks, making them more resistant to head crashes. Hard disks spin whenever powered on, as the system takes a few seconds to reach full speed. Each magnetic surface has a read-write head mounted on an actuator arm, which moves the heads across the disks to read or write data. Usually only one head is active at a time, allowing shared read/write circuitry. The heads float on a thin cushion of air above the disk. They must maintain the right flying height to avoid surface warping, contaminants, or azimuth errors. A special lubricated parking area protects the disk in case of a head crash, though a crash can destroy both the disk and head, often requiring drive replacement or data recovery. Hard disks are made for computer systems where errors are critical. They are assembled in clean rooms, hermetically sealed, and sometimes evacuated to prevent contamination. Despite this, error correction is still needed. Factory map defects are logged so the drive avoids writing to bad blocks. Some drives use heat sinks or helium-filled enclosures to manage heat and reduce drag. Recommended rotational speeds for audio work range from 7,200 to 15,000 revolutions per minute, with RAM buffers used to maintain smooth data flow. Hard disks are connected directly to the host computer for operation. Solid-state drives are high-speed storage devices that use flash memory instead of magnetic disks. Unlike traditional hard drives, solid-state drives have no moving parts, which allows instant data access, very low latency, and silent operation. Data is stored electronically in memory cells, so reading and writing happen almost instantly, making solid-state drives ideal for modern audio production where smooth streaming and fast file access are essential. Solid-state drives are also highly resistant to shock, vibration, and temperature changes, offering greater reliability and durability than mechanical drives. An SSD consists of a controller and a set of NAND flash memory chips. The controller manages how data is read, written, and erased using techniques like wear leveling and error correction to maintain performance and protect data. Unlike magnetic drives, which store data by changing magnetic orientation, flash memory stores data as electrical charges in floating gate transistors. Writing new data requires erasing existing charges, so solid-state drives use algorithms to handle block erasure efficiently. In audio production, solid-state drives provide fast random access, high data throughput, and stable performance even when using multiple tracks or virtual instruments. They avoid limitations like seek time, rotational delay, and head crashes that affect hard drives. Although solid-state drives have historically cost more per gigabyte, prices are falling while capacities rise. Their speed, reliability, and compact size make them the preferred choice for both portable and professional audio workstations. Thank you for watching till the end. To better understand each video, make sure to watch the previous ones. Some may serve as prerequisites for the next. If you have any questions or opinions, feel free to leave a comment. Until next time, subscribe and stay curious.